Okay, before we discuss the answers, I just want to point out a mistake that I made. It's a typographical mistake actually. So I'll correct it now and then I'll upload this. So this is 3, okay. Okay. Similarly here also. Okay. So let's discuss. Okay, the line of sight vector of the transmitter and the user is shown in figure 1. So here we have the line of sight vector and we need to find the unit vector along the line of here we have the line of sight to the transmitter and we need to find the unit vector. Azimuth and bearing and elevation are given. So bearing is with respect to the local north at the user. This is elevation. And this is the horizontal plane passing through the user. This is transmitter. Right. So let's consider a unit vector. I'll denote it as E. Its length is unity. So we can resolve the unit vector into two components. One along the horizontal plane. So that is the projection of the unit vector on the horizontal plane, and the other one is perpendicular to the plane. And we need to find the unit vector with respect to the local navigation frame, NED frame, northeast down frame. And this is the unit vector to the transmitter, so I'll write T, and it should also be resolved in the NED frame, northeast down frame. Right? So this is what we need to find. So if we resolve this vector into two components, along the normal direction we have basically sine theta, and on the horizontal plane we have cos theta. Now since we need to resolve this along the northeast down plane, it will be minus sine theta on the down axis, along the down axis minus sine theta. And then we need to find the north and east components. So for that we need to consider the horizontal component cos theta and then further resolve it along the north and east axis. So this is the cos theta component, and when we know that it makes an angle psi with the local north. This is psi. So the north component is cos theta cos psi, and the east component is cos theta sin psi. Okay. Next, consider the range bearing system shown in figure 2. Okay, we have the figure and the transmitter latitude and longitude are given. User is on the earth surface, so height is 0. Find its ECF coordinates. Earth surface is modeled as an ellipsoid, so we have to use the ellipsoidal model of the earth surface, meaning there are two radii of curvature and bearing is measured relative to local knot at the transmitter and range is much smaller than the radii of curvature. So this can be solved in two ways. This is the bearing measurement and then we have range. I'm dropping the subscript, okay? Psi and R and the transmitter coordinates are uh, latitude and longitude are given. You need to find the user ECF coordinates. What can we do for this one? How did you proceed? Can anybody tell me how you proceed? You can proceed or how you approach the problem? Have you tried or not? Yes.
We have R and we can find the transmitter altitude H using R and angle psi.
That is not x. That is not ECF XYZ. So when you say x, you have to mention in what coordinate frame you are resolving. If you forget XYZ, ECF XYZ, how they are defined and do something, that will not be correct.
And geodetic altitude of transmitter will be different. Other than that will be different from R. So I'm talking about the
Transmitter
angle.
is on the ground. Only latitude and longitude are given, right? Transmitter is on the ground.
Sorry, ma'am.
You need to find ECF XYZ coordinates. So how do we define ECF XYZ? Origin is at the ellipsoid center, right? Let's say here the transmitter is. Latitude and longitude are given. If height is not given for the transmitter, you have to assume 0. Because you cannot assume that the transmitter coordinates are not known. Height of the transmitter is not known. You need to find the user coordinates, not transmitter coordinates. the bearing with respect to the local north at the transmitter. So why don't you pick the north is down frame at the transmitter? If our north is down frame and R is much smaller than the radius of curvature, what does it signify? Can anybody tell me what it signifies? What do you understand by this? If we say R is much smaller, what assumption do you have to make? No response. So nobody understood why that assumption was given. Hmm? What does it mean?
Ma'am, that the distance between the
Hmm.
transmitter and user is r is the same as at the curved distance.
Yes,
The
the
r
straight
distance.
line distance and curved distance, they are the same. The R is much smaller, so you need to assume that the curved distance is actually straight line distance. So this is north at the transmitter, this is east at the transmitter. And let's say this is where the user is. User can be anywhere, right? So let's assume that the user is here with respect to the transmitter and this is the bearing. This is R. So what are the coordinates, north and east coordinates of the user with respect to the transmitter? We have R cos psi and R sin psi, right? And then since the user is on the arc surface, height is 0. So these are the north, east and down coordinates of the user. There is a different notation. R is already used. So I just write some A. Okay. So this is with respect, with respect to the NED frame at the transmitter. North is down frame at the transmitter, and you are also resolving the vector along the axis of the north is down frame at the transmitter, right? Now you know the transmitter coordinates, right? LT, lambda t, and h is 0. So from this, can't you find the ECF XYZ coordinates? You can find ECF XYZ coordinates of the transmitter, right? Now you know the ECF XYZ coordinates of the transmitter, correct? And you also found this vector, but it is resolved along NED frame at the transmitter, correct? We know this vector, but this vector we have resolved in NED frame. Now to do vector addition, what do we have to do? Can you tell me what we need to do if you want to add the two vectors? The transmitter coordinates are given in the ECF frame. This is where the user is. So if you just add the two vectors, the transmitter XYZ and then the user, this vector, in ECF coordinates, we will get the user ECF coordinates, correct? Yeah, the transmitter position in the ECF coordinates, right? We know the x, y, z coordinates. We can calculate the x, y, z coordinate from latitude and longitude. We already discussed this in the class, how to do it. So this is known for the transmitter. And we just need to do vector addition of this one and this one, right? Correct? But this one we have resolved in NED frame. So how will we add that vector to the transmitter position vector? What should we do? What should we do? In what resolving frame we should have that vector A? NUN we have, right? We have calculated ANUN. But to do the vector addition, in what resolving frame we require that vector? You know vector addition, right? To add two vectors, they must be in the same coordinate frame. The components must be in the same coordinate frame, right?
Maybe ECF.
ECF. How will you find it in ECF? Don't you know how to find it in ECF? How can you change the resolving frame? What did we discuss in the class? Is there a way to change the resolving frame? Didn't we discuss this in the class? How can we change the resolving frame? How can we go from one resolving frame to another? So we require this vector in resolved in the ECF frame. How can you change the resolving frame? Did you study attitude? Different methods that we discussed in the class?
And transformation matrix.
Transformation. Who said that?
Muraligan.
Transformation. So what transformation matrix? What do you mean by transformation matrix? What will you do with the transformation matrix? What will you do with the transformation matrix? You said transformation matrix, but how will you use the transformation matrix? Where will you use? How can we change the resolving frame using the transformation matrix? Tell me that.
Ma'am, do we have to find the yaw, pitch and roll angle?
First, to tell me what you will do with the transformation matrix in this context. Then you can find the transformation matrix. First, tell me what why you require the transformation matrix and how you are going to. Suppose you know the transformation and what transformation matrix you require and how you are going to use that transformation matrix. That you tell me. What transformation matrix you require in this context? You said transformation matrix, but why? Why did you say transformation matrix? Nobody can tell me how we can use the transformation matrix to get what we require for the vector addition. Nobody can tell me which transformation matrix is required for this. Have we discussed in the class how we can use the coordinate transformation matrix to change the resolving frame? Have we discussed this or not? Have you studied coordinate transformation matrix or you have not studied at all?
Yes, ma'am.
So what did you study then? You have studied, tell me what you have studied. How you can use the coordinate transformation matrix to change the resolving frame.
Ma'am, we know what the
Forget
role
about
pitch.
role pitch here. I'm not asking about to find. I'm not asking you to find the coordinate transformation matrix. I'm just asking you how you can use the coordinate transformation matrix to change the resolving frame, because you require the vector to be resolved in the ECF frame, right? And you found this vector in the NED frame, correct? On the previous slide, this only you found using the bearing and range measurement. This only you found. So I am asking how we can use, what coordinate transformation matrix we should use, and how to get this one. We already found this one. How we can get this one? This is a simple question. If you have studied coordinate transformation matrix, you should be able to answer. There's nothing big about it. Have you studied coordinate? Yes.
It will require NED frame to Earth center, Earth fixed frame coordinate transformation matrix. NED to ECEF matrix.
Correct. Yesterday we discussed the Euler rotations to go from ECF to NED. Didn't we discuss the Euler rotations? This was an open note test. Did we discuss the Euler rotations to go from ECF to NED frame? Yes or no?
Yes, ma'am.
So we know the Euler rotations, right? And those Euler rotations will give us this. How is this related to this one? Tell me. So from Euler rotations we can get this one, correct? We found that the Euler rotations are functions of latitude and longitude. So we know the latitude and longitude of the transmitter. Using that we can find this transformation matrix. But we require this one. So how will we get this one? How are they related? This also we
Both
discussed in
Ma'am,
are
transpose.
transpose. So we can find this one, right? We can find the coordinate transformation matrix from NED to ECF frame using the latitude and longitude of the transmitter. You already have the Euler rotations, which are functions of latitude and longitude. So by putting the corresponding matrices one after another, you get the coordinate transformation matrix. And that you need to transpose that coordinate transformation matrix and multiply it here. This will give the vector, this vector in the ECF frame. And you just need to add the two vectors to get the user coordinate. In the ECF frame. Okay. This is one way of doing it. The second approach would be the transmitter is here, user is here. Okay. So along north direction, we know we already did this. It is R cos psi. This is along north with the transmitter, and then along east we have R sin psi. Now I just consider the north down section of the ellipsoid. passing through the transmitter. So this is where the transmitter is. So this distance we found. So this distance r cos psi is this. Correct? This is r cos psi. Sujit, are you there? So this white line actually is r cos psi. Let's say this is where the transmitter is. Its latitude is LT. This distance is much smaller. R cos psi. R is much smaller. R cos psi is even smaller. So we can use this for small angle. We can write S is equal to R theta. Or delta S is equal to this is delta theta. This delta S is known. This is R cos psi. So by dividing the radius of curvature north-south, radius of curvature Rn, we can get delta theta, right? Delta theta is nothing but delta L. So user latitude is equal to LT plus delta L. And what is delta L? Delta L is actually delta S by R. What is delta S? Delta S is R cos psi. R cos psi. And what is R? R is north-south radius of curvature at the transmitter. We know that the north-south radius of curvature is a function of latitude, and you know the transmitter latitude, so you can find Rn. R is measured, psi is measured, you can find delta L, and then you just add that delta L to LT. Okay. Now for this one, you need to consider the east-west circle. East-west circle. Yesterday we discussed that the radius of that circle is Re cos L. The same thing has to be done for longitude. Delta lambda is equal to R sin psi by the radius of the east-west circle. So this will give delta lambda. By adding delta lambda to delta lambda t, you will get the user longitude. Now you can do this when r is small, okay? Then only you can do this. Otherwise you cannot. So once you get the user latitude and longitude, we know height is 0, you can find the AC of XYZ coordinates. This is clear to everyone? Yes or no? If it is not clear,
Yes, ma'am.
Krishna?
Yes, ma'am, it's clear.
Okay, the fourth problem is straightforward. Do you want me to solve the fourth problem? Finding the transformation matrix for the pitch rotation. Do you want me to do this?
No, ma'am.
Sujit, did you send the email?
Ma'am, just I send it. Send it already, ma'am.
Okay, how about this problem? What did you do for this problem? How will you find the best and worst geometry? First tell me how many measurements you require. Minimum how many measurements you require? 2, 3, 4, how many measurements do you need here? This is 2D positioning, right? User clock is known, accurate. So there is no user clock error, no prior information. So how many measurements do you require at least to find the user position?
Ma'am, 3.
3. And you need to find the worst and the best set of 3 transmitters, right? The minimum number of transmitters is 3. And you need to find the best set and the worst set. So what criteria will you use to find the best and worst? Did we talk about signal geometry in the class? Did we talk about signal geometry in the class or not? That also you are not able to tell. Nobody can tell whether signal geometry was discussed in the class or not. Have you gone through all the lecture slides at least? Ajita?
Yes, ma'am. The perpendicular signals have lesser common area, so they are better.
Only perpendicular? But what do you mean by perpendicular?
As in, the angle between the lines from transmitter and user should not be very low.
And they should be distributed uniformly.
Yes, ma'am. In this case, 120, 120, 120.
But which one is the worst set and which one is the best? So basically we get a band of circles. There is nothing like true measurement. Measurements are always erroneous. So when we draw the lines of position, it's basically a group of circles, right? Now for each transmitter we get a group of circles. So using the distance between the user and the transmitter, you need to draw those circles. I do not have that PDF in front of me, so I'll just draw a rough figure. Uh, okay, so Something like this will have. Now, how will you draw the circles? So for each line of sight, you need to draw a group of circles and then see how the circles intersect with each other. A rule of thumb is that the circles should intersect almost orthogonally. If they intersect in a skewed manner, the common area, the area of uncertainty will be large. So we are interested in the area of uncertainty. So if you consider this one, let's say we'll take this line of sight, then we will have the corresponding group of circles. This is the area of uncertainty. The lower the area of uncertainty, the better is the accuracy. So we need to find the set in such a way that the area of uncertainty is small, the smallest for the best set and the largest for the worst set. Okay. So in this case, if you do the same, you will find that this one, this TR1, TR1, this one. When you find the common area, the area of uncertainty between these two, from the circles corresponding to these two transmitters, you will find that since they are almost diagonally opposite, they have a large area of uncertainty. Okay, and then you take this one. This will also intersect the circles in a skewed manner. So the area of uncertainty will be large. So this one will give the worst set, and then you pick this one, and this one, and find the corresponding groups of circle. You will find that they intersect one another almost orthogonally. So that will give the smallest area of uncertainty. So basically, I want you to justify your response. Okay, here and then draw the circles and from there conclude which one you think would be the worst geometry and which one would be the best geometry. So even if that does not coincide with the set I mentioned, if your justifications are proper, if your diagrams are proper, I'm going to give you marks. But you should justify why you have picked those sets. If you have picked the correct set but did not justify anything, you will get 0 marks. The justification is important. Any question, anything that you did not get, ask me. Fine, that's it. So if you have any concern, anything that you are not following in the class, you should ask me.